Good evening, everyone. I am doing a nighttime video lecture now because I'm so busy tomorrow. I'm worried I'm not going to have time to do this then. So today is actually just going to be another Excel tutorial. We should have learned in lecture all about this new thing called the T-distribution, which I'm now going to walk us through a little bit more about how we can set up in Excel. And I'm also going to go back. There was an error in my last Excel video. I'm actually gonna take it down and sort of redo things in the last Excel video because I'm worried that the error is very slight, but if people don't hear my announcements about it, they might go through it, put something wrong in their Excel sheet, and ultimately get it wrong in their final exam. So without further ado, without further ado, let me dive in. So these were the two p-values I did for the most recent Excel video, a p-value for paired data and a p-value for non-paired data. And you see our first, so let's do the paired data. This is when we have an x and a y and they have the same sample size and there is some sort of natural correspondence between one variable and the next. And we can calculate a difference between the two of them. So what we do is we take those differences and we just perform inference on those differences. So x bar in this case is going to be whatever the average difference is. Maybe I'll say it's like 0.5, I don't know. Maybe I'll say sigma of 1, 30 observations with an alpha of 0.05. I'm just placing in numbers in just so we can sort of make sure our numbers are actually working as we go through. They're very much made up though. So standard error, that's going to be whatever our value is for sigma divided by the square root of n. Our z-score, similarly, is going to be, it's going to be our x bar, our point estimate, minus our mu. So what's our mu here? Whenever we did these sorts of tests, we were usually interested in whether or not the mean of the differences was equal to 0 or not equal to 0. Which you can actually see that up here in the hypothesis test that I wrote out. So our mu is actually 0, and we want to divide by the standard error to get the z-score. And then if you recall, since this is a two-sided hypothesis test, there's the case when our point estimate, our x bar, is above mu, which is 0 in this case. And there's the case where it is below mu, which again is 0. So if it is in the case where it is above mu, this first one is below mu. So if it's in the case where it's below mu, we want the p-value, it's going to be 2 times the tail probability, which is just norm.s.dist of this z-score, comma 1. And if it is above the mean, we're going to want to do 2 times 1 minus that norm.s.dist. Of the z-score, comma 1. Okay, so it looks like in this case we have an x bar point estimate that is above the mean, so we got a p-value that was pretty tiny. So if we were to see this data that I just made up, it would be evidence towards rejecting the null hypothesis in favor of the alternative. So this was actually the thing down here that I did wrong. So if you did the old Excel video, I would aim, you should be looking at this right now to try to fix it. I made a mistake with my upper confidence interval, so let's be very careful with both of these. You take your point estimate, for the lower you minus a absolute value of norm.s.inverse, so we want the alpha over 2 quantile, the absolute value of the alpha over 2 quantile, which is exactly this. Oh, and I almost made the same mistake I made last time. And don't forget the times by your standard error. Okay? And then the upper confidence interval is going to be the same idea. We want to take our x bar, and this time we want to add the absolute value of our norm.s.inverse function at the alpha over 2th quantile. And again, I will be timesing by the standard error. So this one should be correct. I'm so sorry, there was an error right here, and that's why I'm going to take down the previous lecture video. So next, we have the case where we have two data sets that don't have a natural correspondence with one another, So we have an average from one data set, an average from another data set, and we want to talk about the difference of these two averages. So we have a little bit more inputs. We have maybe the first one was, the average was 30, second one was 31. What's the, if you just look, so this is the average from the X data set and the average from the Y data set. So what's the standard deviation from the X data set? I'll say it's 2, and maybe for the other one it's 4. Standard deviation of Y is 4. Then you want to know what your two sample sizes are. So maybe I got 30 from one and I got 50 from the other. No, they don't need to be the same size. That's very important. And again, I'll just set alpha to 0.05. That's convention, even though it's not a very good convention. So standard error is the one that's really complicated. So maybe watch me closely here. It's going to be the square root of the variance of x, so that's standard deviation squared, divided by the number of values in x, plus the standard deviation of y squared, divided by the sample size from y. And there's our standard error for this value. Our point estimate is just going to be x bar minus y bar. That's pretty easy. So note for the z-score, we have our standard error, but we also need a mu value for the z-score. And again, our hypothesis, our null hypothesis, gives us that the actual population difference between the averages is equal to 0. So that's going to be our mu value here when we calculate our z-score. So I take the z-score that I just, the point estimate, excuse me. Take the point estimate, I minus mu, which in this case is 0. And I divide by the standard error. Get my z-score. And again, we have this thing going on with the p-value that we need to think about, always trying to get the probability of being at or away from the mean. So we're always going to be going towards the tails of the normal distribution. So when the point estimate is less than 0, we're looking at 2 times the norm.s.dist function of our z-score, 1. We're looking at the lower side. And when the point estimate is greater than 0, we instead want to look at the upper tail probability. So we're going to do 2 times 1 minus norm.s.dist, z-score, 1. Okay. And again, let's make sure I don't make a mistake with these confidence intervals like I did last time. So we're going to take point estimate, right? And I'm going to plus or minus that c value times the standard error. So in the lower case, I'm going to minus, the c value is the same thing as last time. It's the absolute value of norm.s.inverse of alpha over 2. So the alpha over 2, the absolute value of the alpha over 2 quantile times the standard error. And then we do the same thing except adding for the upper confidence interval, upper confidence bound. So I'm going to do the point estimate, add absolute value of the alpha over 2 quantile times the standard error. Okay, so these should be correct. I hope I didn't make another mistake. Wouldn't that be funny? The other thing I want to talk about today is we've just learned about this thing, the t-distribution. And I'm going to walk us through, I'm debating how much I really want to do for the t-distribution, because I feel it would actually be a really good exercise for you to figure out some of these yourself instead of just having me walk you through them. So what I am going to show us is I'm going to show us how to do a confidence interval with the t-distribution. And I'm going to set it up in a way, and I'm going to set it up, and then I'm going to kind of encourage all of you to do your p-values on your own and try to go through the notes and figure it out yourself. This will be a really good exercise. I'm worried, I think these Excel cheat sheets are really excellent. I think they sort of streamline your computations and reduce the amount of just, silly computational errors or algebraic errors one might make. But I also worry that if you just have this black box that you make, you might not really think about what goes into it. And I would really like you to think about that. And I think making these sheets yourself is really a good exercise that gets you to think about that. So I'm not going to be showing the p-values for the t-distribution. Try to do it yourself. Try to base it off the notes. If you need help, I'm always open in office hours time. I will do the confidence interval, though. So let's do the confidence interval. we have confidence interval with T-distribution. Okay. That's kind of one. Okay. So what are the things that we need? Just like when we did things with the normal distribution, we still need our X bar, which is the average, sample average. We need our sigma, which is the standard deviation. We need our n, which is our sample size. What else do we need? We need an alpha. Oh, yeah, we do. We do need an alpha. We need our confidence level, right? To get a like 95% confidence interval. So alpha is certainly on there. And I'm actually gonna say, let's move this down a little bit. Let's make a note. The t-test is what we're gonna use when data are nearly normal and sample size is less than 30. So this is the thing that we want to do whenever we have this case. And the reason we want to do this is because we're actually gonna, it's specifically when we have normal data less than 30 and we don't know the population standard deviation. So this is going to be the sample standard deviation. And instead of sigma, I'm going to write it as S. Because we use the t-distribution specifically when we don't know this value. We don't know this value when our data are nearly normal and our sample size is too small to do what we usually do and just predict sigma with S. Since our data is small, sigma isn't a good enough guess. The sample standard deviation isn't a good enough guess for the population standard deviation. So we introduced this new idea called the t-distribution that allows us to kind of circumvent this issue. So these are the things that we need. What are the things we are going to calculate? We're going to calculate the standard error. There's going to be a t-score in there. And then there's going to be a critical value, a C, a margin of error, and a lower confidence interval and an upper confidence interval. Sounds good to me. So these are our inputs. These are going to be our outputs. And I'll just choose some numbers for the time being. Remember, we have less than 30 here, so don't choose an n greater than 30. You should just be using the normal in that case. Let's make it 0.1. Let's break from the norm. 0.05 is antiquated. Okay, so how do we do the standard error? That's just what it usually is. It would just be the sample standard deviation in this case divided by the square root of n. Looks good to me. Our t-score is calculated in the same way as the z-score. Oh wait, did I miss out? Oh, no, I didn't miss out. We just don't actually need a t-score for a confidence interval. Oh, Murph, you're being so silly. My goodness. My apologies, we don't need t-score. I was like, oh my gosh, what's our mu? So we need these. Not that. Okay. So our C is going to be absolute value of the alpha over 2 quantile. So the value on the t-distribution, oh, I almost messed up. The value on the t-distribution whose probability at and below is equal to 0.01 divided by 2. Draw a picture if that sentence kind of shook you a little bit, but it's going to be the t dot inverse function. And we need alpha divided by 2, and then we need our degrees of freedom, which is just going to be n minus 1, just like this. And that's our C value. Pretty cool. Margin of error is just going to be equal to that C value times our standard error. Lower confidence interval. So you remember confidence interval is just point estimate plus or minus this C times the standard error, or plus or minus what we call the margin of error, which is the product of the two of them, right? So we have, for the lower, we're going to have X bar minus the margin of error. And we're going to have x bar plus the margin of error. Just like that, we have a confidence interval using the t-distribution. It's this fun new thing, a new distribution at the very end, the very end of the class. What are we doing? Well, you kind of need to know what the t is if you want to be a literate statistician, so here we are. Okay, so that is this one, and I will leave you to do the p-values on your own, but I would encourage you to come and talk to me and to check it against your homework solutions to make sure you're getting the right thing. Okay, so that's this. The other thing I want to talk about is the other thing that you missed from the lecture video. And if you want to, you can sign off in this case. This is sort of that extra optional topic that I said wasn't going to be covered on the final. But if you're interested in doing inference on the least square regression line, which is the topic that I talked about during our optional lecture, I'm going to show us how to do that in Excel. So what I'm going to do, this was our emails data where we had a bunch of information about the emails and whether or not they were classified as spam. Well, what I'm going to do is I'm going to show you all how to do, first of all, how to build a regression line, but build a regression line specifically with that regression output that tells us whether or not, well, it tells us the error associated with our predictions for beta 1 and beta 2, the population, intercept, and slope. And it also performs that hypothesis test of whether or not our slope should actually be 0 or if it should be something other than 0. So in this case, I'm going to use the number of line breaks in an email to try to predict the number of characters in the whole email. What I'm going to do is I'm going to highlight the data, and I'm going to go to the data tab, and I'm going to press the data analysis option, which is an option that we made available using our toolkit. I think in an earlier lecture I talked about how to make sure you have this. But if you click it, before we were always going to histogram, this time we're going to press regression. And I'm just going to make sure it looks like our output is our y value, and that is B2 to B51. That checks out. The C values are our input. That checks out as well. We don't need any of these. The output range will just tell it where to put it, like where to like put the results. I'll have it put it right there. That's perfectly fine. Let's go ahead and go through it. So there's a number of things it spits out at you. This thing in the middle is called the Anova Table. And it's actually a very significant thing that you will learn in future statistics classes. And it's actually, I wouldn't call this antiquated at all. People still use Anova. But unfortunately, you're going to have to look forward to this in a second level stats class. I'm going to get rid of it for now. You'll note up here we have R squared, which is something we do know about, right? But everything else here we don't really quite know about. And again, I'm going to say we don't need to worry about that. What we do need to worry about, not including these confidence bounds, what we do need to worry about is everything right here. Well, at least I guess you don't really need to, since I'm not going to test you on your final on it. But this is the regression output that we did discuss in the optional lecture. And you'll note it gives you the intercept and the slope. So this is the number we would times by the number of line breaks in our attempt to predict the number of characters, right? So what we have are our values, our least squared coefficients that we get from our sample data. We have this expression of error associated with them. So just like we had the standard error associated with the mean, that gave us an idea of, even though the mean is going to be around the true population parameter, how far away will it vary? And that's the same thing going on here. These coefficients, our guess at the true y-intercept and our guess at the true slope, are going to be around the true y-intercept and around the true slope, but they're going to vary by a certain amount, and standard error is an expression of that variation. The T-statistic is something that we actually should know about by now. It's a t-score, right? We just minus off our mu value, which using a null hypothesis of it being equal to 0, we just minus off 0 and divided by the standard error. So actually, I think if you were to take this coefficient and divide by the standard error, oh, look at that. That is how you get the T-statistic. Funny. That's a really good, actually, Things like this showed up in my qualifying exams. You had to kind of know how everything was interrelated, and it could ask you weird questions, and you had to move things around algebraically. So if you ever want to join me in the PhD program, look forward to things, little things like this. The final thing is probably the more interesting thing for us is the p-value. So note this p-value is very, very small. It is the p-value that is specifically the hypothesis test H0 that slope is equal to 0 versus the alternative that slope is not equal to 0. So you'll note, since our p-value is really, really small, we can pretty robustly conclude that the slope is not equal to 0. And truly, knowing your number of line breaks does say something about the number of characters in an email. It does have that predictive power. So this was the only thing I was going to cover for the optional lecture. You can also, this regression, if you had selected multiple inputs, it would have spit out a multiple regression. Like here, actually, what the heck? This is going to be a long lecture video anyway. Let's give it a shot. I've actually not tried this. Let's see. Let me do 2. No, that's not how to do it. I'm not going to show you how to do multivariate regression, but I think it's also with this regression function. I think for whatever reason, it only takes in numerics, and that's not something I'm going to figure out ad hoc in the middle of the lecture video. So this is it for today. I will see you all tomorrow.